Alright, so in this video I'm going to be explaining another important paper with the title Learning Deep Graph Representations via Convolutional Neural Networks. This paper in 2022 in IEEE. Graph structured data arise in many scenarios. A fundamental problem is to quantify the similarities of graphs for tasks such as classification. Or convolution graph kernels are positive semi-definite functions that decompose graphs into substructures and compare them. One problem in the effective implementation of this idea is that substructures are not independent, which leads to high-dimensional feature space. In addition, graph kernels cannot capture the high-order complex interactions between vertices. To mitigate these problems, we propose a framework called Deep Map to learn deep representations for graph maps. The learned deep representations for a graph is a dense and low-dimensional vector that captures complex high-order interactions in a vertex neighborhood. Deep Map extends convolutional neural networks to arbitrary graphs by generating aligned vertex sequences and building the receptive field for each vertex. So here is an example of non-isomorphic subgraphs, where these are graphlets of size k equal to 3. They are non-isomorphic. So this DGK in reference 9 leverages techniques from natural language processing to learn latent representation of substructures. But this paper just wants to develop a CNN architecture on the vertex feature map. So we analyze the graph structure feature maps of 3 popular graph kernels and then propose definition of vertex feature maps. Then we develop new CNN model deep map on the vertex feature maps to mitigate 2 main issues. Our convolution graph kernels can be based on walks, path or graphlets and subtree patterns. And reference 6 introduces a structure role descriptor for vertices. For example, return probability features generated by random walks, and is then embedded into Hilbert space where the corresponding graph kernels are derived. The graphlet kernel proposed to use the method of random sampling to extract graphlets from graphs. The idea of random sampling is motivated by the observation that the more sufficient number of random samples is drawn, the closer the empirical distribution to the actual distribution of graphlets. So this is the definition of graph feature maps. So psi is this psi, that each entry of this vector is a number of occurrences of atomic substructure A in graph G. So this is a feature map of G. Because we can have different atomic structures like A1, A2, A3, AM. And M is the number of unique atomic structures and depends on graphs. So now we have a good feature map of graph G. A graphlet G is non-isomorphic subgraph of size k. And let G be the multiset of size k graphlets. Then for graph G, its feature map is defined like this. So M here is the number of unique graphlets of size k. So once we have this feature map, then we are ready to move on. And There are many ways you can create these feature maps, but the feature map of WL Weisman-Lera is the concatenation of feature maps at all iterations. So we develop a new convolutional neural network for learning deep graph feature maps, which is called deep map. Here we define vertex feature maps. Define a map psi, such that psi of V and A is the number of occurrences of atomic substructure. A contains V in the graph. The feature map is invariant to the ordering of vertices and size of the graph. This is very important property. If you want to work on equivariance, the permutation invariant properties. So this is one of the most important tools that you can have. Because you're summing them, so it doesn't care about the permutations, and each phi of y it has a feature map for each vertex, which is based on the structure of the graphs and these atomic substructures. So we have created a very feature permutation invariant measure for the graph. And then if two graphs are isomorphic, their deep graph feature maps after the summation layer are the same, which is a good property. So the algorithm is very simple. Once you have given a set of graphs, corresponding labels, and the size of the receptive fields, the output is the classification accuracy. So we have feature map initialization, and so here we use breadth first search, starting from V on original graphs to find the top R-1 largest neighbors with respect to eigenvector centrality vector values. But this is just one approach. You can define your feature map in a different way. This is an illustration of the generation of vertex sequences and the corresponding receptive fields for undirected graphs. And you see, finally, you have these convolutional architectures. M is the dimension of vertex feature map, W is the number of vertices, R is the size of receptive field. And they did experiments on these data sets like NCI1, proteins, enzymes, IMDb binary and multi. So we use them for graph classification. And if you compare it with deep map, you see most of the data sets, this approach of deep map outperforms other approaches like graph isomorphism network